Okay, good afternoon, 61C. I was going to say a bit of Murphy's Law in St. Paddy's Day, so Adobe killed my PowerPoint, I think it was. Anyway, so let's see if we can get going now, a little bit late. Okay, so we're going to keep going, talking about caches. So just to remind you where we are in the stack, we're in the memory system over here, where it connects the cores together, connects the cores to memory. So today I actually want to go a bit slowly back over some of the cache stuff, try and get your mind straight about stuff, and then also talk about multi-level caches. But just to review what we did last time, so we talked about cache organizations, direct map versus set associative versus fully associative. We introduced this time model of how long a memory access takes on average when you have a cache, the average memory access time. Simple formula is it's the hit time plus the miss rate times the miss penalty. We also talked about categorizing the causes of misses, where the misses come from. And we had this categorization of they can be from compulsory, capacity, or conflict misses. Then we also started talking last time at the end of the lecture about the effect of cache parameters on performance. And so this time I want to actually go over that a bit more detail about how these different cache parameters affect performance. Hopefully also sort of review all the different cache organizations as well while we go in there. So there's sort of three primary cache parameters. There's sort of important things you first need to know when talking about a cache. First is the block size. So how many bytes of data are there on each line in the cache? So each entry in the cache, we call these blocks or lines. I'll tend to say line, the slides tend to say block, but both words are used. So each entry in the cache has some amount of data, some number of bytes, as well as the tag and the valid and dirty status bits. So one thing you need to know is what is the block size, because that is the unit of transfer between the cache and the main memory. It also influences a lot of things like how big the remaining fields in the address are when you're indexing the cache. The second important parameter is the associativity of the cache. So the associativity tells you how many different places you have to look in a given set in the cache to see if there's a match. And so this is the associativity equals a number of ways in each set. And you have two extremes. Direct map case, there is only one way in each set. So you only have to check one tag to see if there's a match. The other extreme is fully associative. So you search every entry in the cache to see if there's a match. So you have to look at all those tags. And the middle ground is the most common, is a set associative cache, where you have some number of sets, and within each of those sets, there is some number of ways, right? So it's kind of a trade-off between the two extremes. Now, the other very important parameter is the total cache capacity. And you can get this from just knowing the total number of entries in the cache, how many lines are there total in the cache, multiplied by their block size in bytes. And another way of getting out the number of entries is look at the number of sets times the number of ways, and that'll tell you how many total lines you have in the cache. So an entry is the same as a line, is the same as a block, right? So these are the primary parameters that set caches, and in first order, when you're understanding a memory hierarchy, these are three things you want to know about every piece of the memory hierarchy. Now, there are a lot of other more detailed parameters, and we'll talk a bit more about two of them right now. One is the write policy, how are writes handled, or stores, how are they handled in the cache system. And then also the replacement policy, which is what you do when you get a miss to select which line you're going to kick out. Because remember, you always have to kick out a line if you're bringing in a new line. The cache has finite fixed capacity. So let's talk about write policy choices. We talked a little about this. I just want to go in a bit more detail this time. And when you're looking at writes, the policy decisions break down into two cases. What do you do when you get a hit? And what do you do when you get a miss? When you're processing a write to the cache. So when a store instruction is trying to write some data item in memory. So on a hit, the two decisions you can make are make it a write-through or a write-back cache. Right, and those we talked about before. So on a write-through cache, every time you access the cache, you update the cache if you get a hit, but you always also send the value to memory. And remember, you had to add a write buffer there to make sure the CPU wasn't always just stalled on that write going out to main memory, right? So you kind of decouple, let the CPU post the write to that buffer and keep running, but in the background you have to drain that write out to the main memory. So a write through cache always tries to write to the cache and always updates the main memory at the same time on a cache hit. Conversely, a write back cache only tries to update the cache and doesn't update the main memory. So you just look in the cache. If you get a hit, you just update the data value inside the cache. And at that point, the main memory is going to be stale. So it's going to have the old value of that location. And so they'll be incoherent. The copy in the cache versus the copy out in main memory. The correct version is the one in the cache, right? You just wrote to that one and not to main memory. So the only way that memory actually gets updated is when you have a line to which you wrote. And remember, in these write-back caches, you have a dirty bit that you set. So any write to the cache line will set this dirty bit. That indicates that later on, some point in the future, some other access is going to get a miss, bring in a line, and as a side effect of bringing in a line, you're going to kick out this line that has the dirty bit set, and that's the only way that the updates will get propagated out to main memory, right? So you only do the writes to main memory when you evict a line that has dirty data. Okay, that's the only time memory system gets written to. So just comparing these two choices for hits, write hits. The write through is actually a much simpler scheme because you kind of always do the same thing. You just always write to memory, and on the side you check the cache. If there's a hit, you update the value. If there's a miss in the cache, you're done. You've already, sent the value to main memory. You don't have to worry about anything usually. In the write back case, though, it's a little more complicated. You have to first do the write in the cache, and depending on what happens, you may have to do 0, 1, or 2 memory accesses. You do 0 accesses if it's a hit, you just update the value in memory. You do 1 access if it's a miss and you evict a clean line. You do 2 accesses if it's a miss and you evict a dirty line. And this complicates the way you build the pipeline around these write-back caches. But the benefit of the write-back cache is generally they involve less traffic to the next level out in the memory system. So imagine you writing the same location repeatedly. So you have a loop and some variable you're updating repeatedly. A write-back cache, none of those writes will make it out to main memory. But a write-through cache, every single time you write to that location, you're going to also send it out to main memory. So the other part of the story is what happens on a miss. And there's actually 2 choices here, which is what we call write allocate or no write allocate. Basically, when you miss on a store in the cache, the 2 choices are, if you do no write allocate, you just send the word off to memory and you update that value in main memory. A write allocate, though, instead of doing that, what you do is bring in the whole line from memory, read in the line that you're going to be writing to, bring that into the cache, so you're allocating a block in the cache, and then you update a piece of that line, the piece you're writing, in the cache, right? So write allocate means allocate in the cache, right? So when I get a write miss, first read the old data from memory, put it in my cache, and then update it in the cache and set it to be dirty, right? That's a write allocate policy. Now, theoretically, you could mix write allocate or no write allocate with either of write through or write back. In practice, though, they kind of always are put together in these combinations where a write through cache does not do write allocate, because that's the simple thing to do. So the write through cache, if you miss in the cache, you're already writing to memory. So there's no reason really to bring the line in and then update it. You're going to be writing it to main memory. So that's the simple combination there. With the write back cache, you almost always do write allocate. So with the write back cache, if you get a write miss, you first bring in a clean line from memory, put that in your cache, potentially, you're going to kick out some line from memory, and if that line was dirty, that will get written back. But then you bring that clean line into the cache, and then you update a piece of it and set it to dirty. So that's the usual thing you do if you have a write back cache. Yep, question?
How do those times compare then? Because it seems like the no write allocate is slower than write allocate, but write through is
Sorry, I didn't quite hear the question.
Or how do those the times compare to like write?
How does the time compare? So you're asking which is faster, or? Yeah, so it's not an easy. It depends. Is the fortunate answer. These are choices that are you'll find systems that use both of these schemes, and in one system, you may have one system uses both of these schemes in different places, depending on what's happening. I'll talk a little about that later. So at first off, you might say, well, the write-back cache is obviously better because it's sending fewer writes to memory. However, to make that simple to design, you usually have to do more reads to read old blocks that you then overwrite and then send back. Right? And you might imagine, so there's no reason you have to have these combinations. For example, if you had a write-through cache with write allocate, what that would do is write to memory, write to the cache. If you got a miss in the cache, bring the line in to the cache. Why would you ever want to do that? Why would you even think that might possibly be a good idea? So you're writing to a line that's not in the cache. I'm going to read the whole line into the cache first before I do the write. Yep. Right, so locality, whether it's temporal or spatial, right? So you might say, well, actually, if I got a write miss to that line, it's highly likely that I'm interested in data around there, so maybe I use that as a hint to bring the line into the cache because the next request may read something from that line, right? Notice it will only help you with reads, because writes, you have to write through to main memory anyway. But if that write to that location is a hint that possibly you'll read something, it may be worthwhile doing write allocate and bringing it in. Let's look at the other oddball combination. If you do write back with no write allocate, what that means is if I do a write and I look in the cache and I get a miss, instead of bringing the old line in from main memory, or clean line in from memory, then updating it, I'm just going to send the word out to main memory, right? So don't bring it into the cache, just send the word out to main memory. So what's good about that combination? Why would you consider that combination? Write back with no write allocate. Why might that be a good idea? Yep. Right, so you can imagine that could be faster because I don't have to wait to fetch the clean line from memory before I proceed and update it. I can just ship the write data off to memory and forget about it. I buffer it up in the background, right? So it's not obvious. In any given case, you would do performance experiments and simulate the combinations to see which you should use. The reason these are the common combinations are these involve the less hardware, the least amount of hardware design. Because the write-back cache already has to fetch lines from memory, update them in the cache, and send dirty data back. If you provided no write allocate, you'd have to have a different mechanism of sending a single word to memory all by itself. Because otherwise, in the write-back cache, you only ever read and write whole lines to and from memory, right? So making it no write allocate means I have to handle single word at a time or single byte at a time accesses to main memory. On the other hand, write through with no write allocate, that's kind of what write through caches do naturally. So you don't need any additional mechanism to, if you add write allocate, that adds a new thing that the cache has to do, which is bring this line in on the write. Okay, so write through with no write allocate, write back with write allocate. Those are very common combinations. You can almost assume that's what's happening when people tell you to have a write through or write back cache. So another piece of cache design decision is the replacement policy. Okay, so remember, so why don't you need a replacement policy in a direct map cache? Let's start with that. Why is it only in a somewhat associative cache you need a replacement policy? Yep. Right, exactly. So the direct map cache, there's only one place the line can go, which means there's exactly one victim that is going to get kicked out regardless, right? If there's only one place you can put it in the cache, whatever was there before is the victim. You don't need a replacement policy because there's no choice to be made. So you only need a replacement policy when there are multiple ways in a set, and you get to pick which of those ways are kicked out to make room for the new item coming in. So we talked a bit about some of the policies, and there's a few different ones. I put a few more up here. Random is one we talked about. Just pick one at random and throw it out. Least recently used is trying to exploit temporal localities. The intuition is try and pick the thing I haven't touched in the longest time because it's probably the one I'm least interested in. Or conversely, things I've touched more recently are more likely to be touched again. That's the principle of temporal locality. And we talked about how it's easy to do that exactly if you have a two-way cache. You just need one bit that says, which way did I access recently? The other way must be the least recently used bit way. It gets a lot harder as you go to more ways. So people often use what are called pseudo-LRU, which kind of approximate LRU, in order to reduce the complexity of the hardware. So one thing that's mentioned on here is a binary tree. And this is a simple idea of, instead of having a complete ordering, you divide the ways into a binary tree. And so one bit says, is it the left side or the right side of the tree that was least recently used or most recently accessed? Then within that, whether the left or right subtrees were most recently used. So if you have a four-way cache, you only need 3 bits. So one bit of the root to say, is it those two or this two that were most recently touched? And then each of those two individually has a bit that says, was it that one? That's the 0 or 1 or 2 or 3 were the least recently used. And so that's just an approximation of LRU. It's not completely accurate, but it's good enough to help performance. When you have a very large cache, fully associative cache with many entries that you search, it's actually very difficult to do anything that's really like LRU. And so people often just do a very simple round robin. And when you have a highly associative cache, that tends to work pretty well because the chances of kicking out the wrong thing drop as you have more ways, right? So the chances of picking the worst ways to kick out goes down once you have more ways. You just have this round robin going around. And if you do pick the wrong one, all that will happen is you'll get a miss, bring it back in again, and kick something else out. So it kind of self-repairs if it makes the wrong decision. So you might get a few more misses than the perfect case, but it's not that bad once you have a lot of ways. And, computer architects spend a long time futzing with this stuff, so there are thousands and thousands of these schemes. Another common thing is this idea of not most recently used. Something like a FIFO scheme, but make sure you don't pick the one that you just touched, right? Not the one I just touched. If the pointer is at that guy, move another step and pick the one after that, right? Now, the thing about replacement policies, it can be somewhat important, but they're all a second-order effect, and the reason is that you only use these on misses. Right? The replacement policy is all about what happens on a miss. And with reasonable caches, the hope is that most of the time you're getting hits. And if you get it wrong, it will sort of fix itself the next time around, right? And then you'll hold the thing in cache, right? So replacement policies are good things to ask questions about and important things to have in designs, but they're really a second-order effect compared to those primary parameters of how big is the cache and how many, what's the line size and what's the associativity. Those are much more important factors in performance. Okay, so we talked about the parameters, including these smaller design details. We also talked about the different way of categorizing misses, there's 3 C's. Compulsory misses, these are the ones that, you've started the program up, it's never seen that location before, so the cache doesn't know to have it in the cache. So we call those cold start, first reference, compulsory misses. You kind of have to miss the first time you see them. And, in the grand scheme of things, these are usually not that important because you have long-running programs, and this is just a warm-up when the program first gets going. And after that, those first few misses don't really matter across the whole run of the program. Capacity misses are where basically the cache is just not big enough to hold the data you're working on. And one way of thinking about these are misses that you wouldn't get if you had an infinite cache, right? If you never had to throw anything out, you would never get capacity misses, right? The capacity misses are there because, caches are designed to be small and finite, and you have to replace things. The final category is these conflict misses, also sometimes called collision misses. And these occur because you have a less than fully associative cache, and so locations are competing, memory locations are competing over a given set in the cache. So multiple memory locations map to the same set. And so one way of thinking about these are misses that you wouldn't get if you had an ideal fully associative cache. Right? They're a consequence of using some reduced associativity, which you do to reduce the hardware cost. Okay? So the 3 C's, compulsory, capacity, conflict. Okay, so what I do now is kind of revisit what we did last time a little about the effect of these parameters on cache performance. And we had this formula for AMAT, the average memory access time. So that's the hit time plus miss rate times penalty. I saw a few posts on Piazza. People were asking about why isn't it, why do you always have hit time? Why isn't that hit time times 1 minus miss rate? Well, the reason is, like we talked about last time in lecture, you always search the cache first. So you always pay the hit time to figure out, do I get a hit or a miss? So the miss penalty is added on top of that. And the miss rate is how often do I get this additional penalty because I got a miss, right? So view it as the hit time is the base cost that you always pay. The miss penalty is the additional cost that's only if you get a miss, right? And the miss rate tells you how often you're going to pay that penalty, whether it's in cycles or nanoseconds or whatever. Okay. All right, so I want to change gears a little. We talked a lot about cache parameters, a bit in the abstract. I want to put it back in the context of our processes, and where does the cache fit in the processor pipeline, and how does it interact with the processor pipeline? So what you see here is sort of a version of our classic five-stage pipeline. Here's the instruction fetch stage. Here's the program counter going to the instruction cache, fetching instructions, decoding, executing. Here's the data cache, and here's the write back at the end, writing back to the register file. Now, when we first talked about pipelining, we just drew these as ideal memories, the instruction memory and a data memory. And once you replace those with caches, you can actually build something that is almost ideal. Like the instruction cache usually only takes 1 cycle to access, but occasionally you'll get a miss, go off to the big main memory, fetch those instructions. So you can run programs as if you had a big main memory that ran at roughly 1 cycle. It'll just be a bit slower than 1 cycle because of the misses. Same with the data cache. It fits in 1 clock cycle here. Now, when you do get a miss, what's going to happen is there's a signal going to come out of a cache to say, I got a miss. And the control logic for the pipeline is going to have to stop what's going on and wait for the data to show up from memory. And that's what we call a blocking cache. That's one reason I don't like to use the word block for cache line, because one other use of blocking caches is the cache blocks, i.e. it stalls and is waiting for something to happen. So say you did an instruction fetch and you got a miss. There's really nothing you can do in the pipeline until you find out what that next instruction is. You have to wait for the instructions to be fetched from memory, place the instruction cache, then you can restart and redo the fetch and get the instruction down the pipeline again. Now what I'm showing in this design is when we get a miss, or not a hit, we're going to put a bubble down the pipeline. So you have to tell the rest of the pipeline to do something when the instruction cache gets a miss. So the idea here, we just put a bubble in. And so that means the rest of this pipeline just keeps running and drains out, while the front end, which has the instruction fetch stage in, is waiting to get instructions from memory. Okay, so you're just putting bubbles in while waiting for this to come back. So notice the refill data then come from the low levels of the memory, be written to the cache, and then you can retry this instruction fetch and then finally get the instruction and keep executing. Now the data cache side, this happens a lot later down the pipeline where the memory stage is. So in that memory stage, when I do a memory access, I put the address in, and if I get a miss here, I'm actually going to stall the entire CPU. So everything in the pipeline is going to be stalled. So why do I have to stall everything in the CPU when I get a data miss? Yep. So it's possible you might have a data dependency. So that value you're loading from memory, the following instruction needs. But remember, in this pipeline, there's a load use delay of 1 cycle. So the instruction right behind it cannot be dependent on it. You wouldn't have let it go down to that stage. So what's another reason you have to stop everything when there's a data cache miss? What would happen if you didn't stop everything? Yep. Right, the thing right behind you come tearing into you and just ruin your logic. Like you have to stop because the instruction that's in the data stage cannot proceed. You're executing instructions in order. You cannot have the other guys flow through this stage and do memory accesses while somebody's in there waiting for a data cache miss to come back. So you kind of have to wait and hold everybody off so they can all go through that memory stage in order, right? And also, there's only space in each pipeline stage for one instruction. If you try to emit the next instruction, you would lose all the state of the one you were executing. So you kind of have to just stop and freeze the entire pipeline. And the way you freeze the pipeline is basically each of these registers in the pipeline has an enable signal that says whether they should actually update on the next clock edge. And when you see you get a miss, you just disable all the registers from updating so they won't update when there's a next clock edge. And so the pipeline won't advance, it'll just stay put. While off to the side, you're fetching data from memory and refilling the cache. So it's almost like when the data cache misses, you freeze time for all the instructions in the pipeline. You don't even know anything happened. You kind of just magically stop time for the processor, go get stuff from memory, bring it back in. Then when it's ready, you then restart time on the main processor by allowing all the registers that are clocked to update. So a good question is, well, why don't I just do that for the instruction cache miss too? Right? Why don't I just freeze time to get an iCache miss? Would it be correct for me to do that? Would it be correct to just stall everything while I do an instruction cache miss and then restart it when it comes back? Yep.
No, because the instructions before the miss can still carry on through the pipeline.
So the response was no, the instructions before the miss can carry on through the pipeline. Well, if I freeze everything, they can't move. They're stuck, right?
Correct, so that's why you don't freeze it.
So the question is, if you freeze it, would it be correct?
Well, it just seems unnecessary. Like, those instructions that are currently operating don't depend on the new instructions, so they can just keep finishing. Like, you don't need to stall the rest of it.
Okay, but is it correct to stall it? Would it give you the right results? Yeah, it would. So it would. If you froze the whole machine, you would get the right answer. So the question is, why do I let the other ones proceed? And like you said, those instructions that are down here in the pipeline, they don't depend on this. They are older instructions from earlier in the program. They don't depend on this new instruction that got an iCache miss. So it's okay to just let them continue down the pipeline. Right? There's no reason to stall them. Is there any benefit to not stalling them? Would it make your program go any faster to let those finish while I'm waiting for this instruction cache miss? Would there be any benefit? Yep. So why would it be slower?
No, it'd be slower to process.
Right. Okay. So why would it be? Okay. So if it's faster to let them proceed, in what case is it faster? Given that you have to wait, that instruction has to wait anyway for the instruction fetch to come back. Where would you be saving time? Yep. Right, so it comes down to those other instructions may actually have other reasons to stall, and you can overlap two of those stalls. So an instruction may get a miss in the data cache, and you can overlap that with the iCache miss, or the instruction might get a cache hit in the data cache, but it was right before the following instruction that caused the iCache miss, used the value in the load and would have got an interlock. So you would have got two interlocks. Once when you stole the pipeline for the iCache miss, then once it moved to execute, instruction and data cache, there'll be a load use dependency and have to wait. So generally it's a good idea if you don't need to stall instructions, let them complete, because then you may overlap some other hazard resolving with that, with this instruction cache miss resolving. Okay, but this is a very simple structure for the CPU where you're just going to freeze everything on data cache miss, insert bubbles on an iCache miss. And in both cases, those caches can only do one thing at a time. Just wait to finish that request. More advanced processors, the caches will actually overlap multiple misses in flight to try and speed things up. But for now, just worry about this, the 5-stage pipeline. Okay, so just for the next few slides, I just want to go back over the, sorry, question?
The way we get
okay, so this is really a question about logic design style. If I have a register and I want to have it freeze its value, there's two ways of doing that. One is that the register itself, the circuitry usually has an enable signal that says, don't update when the clock edge comes in. An alternative is, if you don't have that, you can just have a mux that feeds back the output back to the input, and you just recirculate the old value using the mux. So you clock the register. So you can, both those ways are valid ways of building a register that doesn't update on a given clock edge. Yeah, both of those will work. Okay, so now I just want to go through the effects of the parameters on performance. So basically, what happens when you increase block size, and how does that affect AMAT, right? So what happens to the hit time as you increase the block size? So remember, AMAT is hit time, miss rate, miss penalty. So what happens to hit time as you increase the block size? Yep. It increases. So why would it increase? So that's kind of the obvious answer. And you might think, well, if it's a larger block, it's going to take longer to access. But if the memory is the same size, you just divided it up, the blocks. Yep. Why would it decrease? Okay, well actually the way you organize, this is actually a very common misconception, even amongst people who should know better. But when you build a memory to hold the data for a cache, it's usually just the same shape memory, regardless of the block size. All you care about is how big are the accesses I need to make. Do I need to get a word out at a time or a byte out at a time? And so the storage, the actual circuit looks the same. It's just whether you have address bits, how many address bits are relevant to selecting a block versus a piece within a block. The actual storage, if the capacity is the same, the RAM will look the same. Okay, so you'll read, 32 bits in and out of a structure that has enough bytes to hold all the capacity in your cache, or a piece of it. So actually, the access time of the RAM only really depends on how big it is total, the total capacity of the RAM, not how you've divided it up into blocks and tags. And the one thing that might cause a slight reduction in hit time is if you have larger blocks, you'll have fewer tags. And so the memory that holds your tags can be smaller, and so you might get some saving there because you're reading from a smaller array that holds the tags, because longer blocks will reduce the capacity you need to hold the tags. Okay, but that's a small change. Okay, how about the miss rate as the block size increases? Right, so increasing the block size, how does that affect miss rate? Yep. Right, so if you increase the block size, that's right. So you expect it to go down as you start from one word and start increasing the block size, because you're going to get spatial locality, and you're going to bring in words you didn't ask for, but it's highly likely you're going to need. And so that will mean the number of misses you need will go down. But what happens if you keep increasing the block size? What if I have one block for the whole cache? Right, so the problem is there's sort of a trade-off. As I first start increasing it, my miss rate drops. But as I keep increasing the block size, I have fewer and fewer blocks in my cache. And at some point, in a degenerate case, you just have one block that's your whole cache, and that's going to perform pretty badly. So the answer is it goes down at first, then it goes back up again when you have increased conflict misses. How about miss penalty as you increase the block size? How does block size affect the miss penalty? Yep. Yeah, so generally the miss penalty is going to go up because, remember, the longer the block you have, that's the unit of transfer from the next level out of the memory hierarchy into the cache. So generally I expect if I increase the block size, it's going to take longer to get that data from the next level out. Now, one thing to be aware of, though, there's usually a fixed latency cost for getting any data from the next level. So you kind of pay this large sunk cost just to get anything from the next level out. And so going from 1 word to 2 words probably doesn't increase your time that much, because a lot of it's just the time to get the first bit of the first word, and the other bits can follow pretty quickly after you've did the initial request. But eventually you'll find you will be limited by the time it takes just to transfer all the bits. But there's a large fixed overhead just in that initial access. So it actually makes sense to do longer blocks because you already paid for that hit time. So this is a trade-off that you make. You want the block size to be long enough that you amortize that first access to the next level of memory, but not so long that you get lots of conflict misses in the level of cache you're in, right? Because you don't have enough blocks. Okay, other parameter, associativity. So, yep, question?
For the time, if you increase the block size, do you not have to take into account like the time it takes to choose which part of the block?
Well, it turns out you can, the bits that select the set and the bits that select the word within a block, the RAM doesn't really care which of those bits, whether those bits are in the set index or in the block offset when it's reading from the RAM. So that's why you have the same shaped RAM and you're changing this parameter. All you're really doing is saying more or less of these bits are in the block offset or in the set index. So the memory doesn't really care, and so it runs at the same speed. Okay, so increasing associativity, how does that affect hit time as you increase associativity? Hit time, associativity increases, yep. Right, so it goes up because you have to look at more tags, and then once you look at the tags, you have to select the right way to produce the value. And the thing with associativity, there's a big step from direct map to two-way. So going from direct map to two-way, all of a sudden, data may come from more than one place. The nice thing about direct mapped, even before you've done the tag check, you know where the data is going to come from if it's in the cache. So you don't need to have a mux at all on the output. Whereas if you're doing a set associative or fully associative cache, you first have to check the tags, and depending on those results, you pick some data to mux out to the processor, right? And then after that, there is a slower increase as you add more ways. You add a little bit more delay for each level of associativity, but the biggest hit is going from direct map to two-way. How about miss rate as you increase associativity? Right. Yep. Okay. So it does go down, but what's the big reason you add associativity? Yep. Right, because you get less conflict. So there's less chance of conflicts if multiple things can map to the same set, right? So yes, the miss rate goes down. One thing you'll see is that the big benefit is going from one to two-way or two to four ways, and after that, you really get diminishing returns for making it more associative. Yep. Well, really, associativity only helps with conflicts, right? It just lets you put more blocks that have a bunch of address bits in common and have them co-resident in the cache at the same time. It really is only about that. It's really only about conflicts. It doesn't really affect the spatial temporal locality of the blocks themselves. The blocks haven't changed in size. The capacity hasn't changed. It's really just about conflicts, about which locations in memory can live in the cache at the same time, right? So associativity helps that. But like I said, like you get the big jump from 1 to 2 to 4, and then after that, it's really diminishing returns. So one thing to notice here, it's kind of awkward that direct map caches are really fast, but they suffer from a lot of conflict misses. But as soon as you go to associative, you get a big penalty in hit time, but you do get a big improvement in miss rates. You have to trade off hit time and miss rate in those caches. How about miss penalty as associativity increases? So increasing associativity, what's that going to do to my miss penalty? Yep. Right, it's not going to change. Right, associativity is really all about where things live in the cache. It doesn't really affect how long it takes to get stuff from the next level out. So it really doesn't change at all. You might say, well, you might have a complicated replacement policy, but the replacement policy usually runs in parallel with when you get a miss, what you usually do is go get the thing you missed on first, because that takes time to get from memory. Then, while that's going on, you figure out which thing am I going to kick out, and then kick it out after you've started bringing in the correct line in. Okay, last one of these. So increasing the number of entries. If I increase the number of entries, I'm adding more blocks of the same size to the cache. So what happens to hit time is I increase the number of entries. This one should be easy. Making it, sorry? It's unchanged, let's add more entries. What happens when I add more entries to the cache? Gets bigger, right? The cache gets bigger, all the memories get bigger, so it's going to take longer to access. The memory structures are bigger. I have more entries now. So what happens to the miss rate as the number of entries increase? Decrease, right? I made my cache bigger, so all the capacity misses should go down. Also conflicts. So actually one thing to talk about is there's a rule of thumb that architects use on capacity. So if you want to cut cache misses, one easy way to do it is make your cache bigger, right? But what you find is, remember we talked about this last time, there's a lot of locality in the first small cache you put in, and it's, as you add bigger and bigger caches, there's less locality to exploit. And the rule of thumb, and this is a strange empirical observation, is that it's basically the number of misses drops as the 1 over the square root of the cache size. So if you basically want to half your miss rate, you have to make your cache 4 times bigger. And nobody knows why this is. It's just when people look at programs running, this is kind of what falls out. There's kind of this power law relationship that sort of 4x improvement in cache size gives you a 2x reduction in miss rate. And so basically you have to, that's why at some point it doesn't make sense to keep growing your cache. You have to make it really big to get a small reduction in miss rate. What happens to the miss penalty is you increase the number of entries. Miss penalty is you increase the capacity of your cache. Made your cache bigger, what does that do to the miss penalty? Nothing, right? Doesn't change. Like the time it takes to get memory doesn't really affect, you're not affected by how big this level of the cache is. Okay? All right, that's unchanged. Okay. All right, that was a big hard slog, but I was trying to be pretty exhaustively going through all the cache parameters and how changing one at a time, how that affects the components of the access time. Let's do a bit of administrivia. So project part 2 is due March 22nd. It's spring break next week, and we're not assigning you any work over spring break, so you can have a true break and work on assignments for all those other professors who do set you things over spring break, I guess. So the next assignment, homework 5, will be due April 5th. There'll be a midterm the week after the spring break. And if you have conflicts, email Sarah, and we'll send email about DSP accommodations as well. Let's take a 2 or 3 minute break. I think you've earned it. Okay. Okay, let's get started again. So one of the things, if you notice all those techniques, we didn't really have much that we could use to reduce miss penalty. We had tricks to, you could play with hit time and miss rate, but miss penalty. And if you think about our earlier lecture where we talked about it might take, several hundred clock cycles to go to main memory. That's really quite long. And so people started thinking maybe there's locality in the misses from a cache. So we often usually think about locality from the initial program accessing the cache, but then the cache itself accesses main memory. And is there locality in the misses from a cache going to main memory? And the answer is yes. And so because of that, you use the idea of caching recursively, right? So if it takes too long to go to main memory, put a cache in the way between the level 1 cache and main memory, add a level 2 cache. And so, as transistor scaling has continued, we've been able to put more and more transistors on a chip. And if we just use those to make a single level of cache that was as large as the whole chip, it would be very slow. It takes a long time. As you scale things down, proportionally, it takes a long time to get across chip to access all of memory. So you don't want to just put a huge single level cache on the chip. That would just be way too slow. And so you're motivated to add more levels of cache where each level gets bigger and bigger. But the idea is most of the accesses are still coming from the innermost levels of the cache. So in lots of cases these days, there's actually a level 3 cache on chip as well. So there's 3 levels of caching on the chip. We have that many transistors, we actually have to break it down into 3 levels of cache. And some machines even have a level 4 cache. Usually that's off chip. So I'll go an example later about an IBM mainframe where you have order of a gigabyte of cache off chip. And in these systems, you may have hundreds and maybe even terabytes of main memory in the system. Okay, memory hierarchy. Just review. You've seen this picture before. So basically, the idea of memory hierarchy does recurse down. You can keep using this to go from level 1 cache, level 2 cache, level 3 cache, level 4 cache, so on down to level N. And at the outside, you have the main memory, which is DRAM in modern systems. But even then, that extends out to, we'll talk later about virtual memory, where you use DRAM as a cache of things you hold on disk or flash, right? So as you go down or out from the hierarchy, the size grows and the speed drops, but also the cost usually goes way down as well. Now, when people talk about levels in the memory hierarchy, you'll hear people talking about upper and lower memory hierarchy. Unfortunately, people use those to mean exactly the opposite depending on who you speak to. Some people think upper is close to the processor. Some people think upper is those levels with a bigger number, right? Level 3 is more upper than level 1, right? Other people think upper is closer to the processor. So up and down doesn't make sense. So I always like to use inner and outer, because that to me is unambiguous. So inner is next to the processor, outer is further away, right? So I always like to say inner and outer levels of the memory hierarchy. And as you go further away from the processor, they get slower in terms of latency. The time to access will grow just because of physics, okay? So back in lecture 11, I had an in the news item about this latest IBM mainframe. I like to use this because it's brand new, and it's one of the biggest chips out there, and it has some of the most advanced fabrication technology, 17 layers of metal fabricated on the chip, 4 billion transistors, 8 cores, and it has this memory hierarchy. So I mentioned this back then, but I didn't show any pictures of it. So here's some pictures of this IBM mainframe chip. So what you're seeing here is the memory hierarchy on this chip. So each of the 8 cores has this structure where they have 96 kilobytes of instruction cache, level 1 instruction cache, and 128 kilobytes of level 1 data cache. So that's the innermost piece of the memory hierarchy for each core. Now in this processor, each of the instruction and data has a second level. It's actually split at the second level. A lot of systems have it unified at that level, but in this system it's still split. So there's 2 megabytes of level 2 instruction cache for the core, and 2 megabytes of level 2 data cache for the core. The next level out is a shared L3 cache. Shared means there are 8 cores on this chip. There are 8 independent processors on the chip that run in parallel. They each have their own independent level 1 and level 2, but they share this large level 3 on the chip. And that level 3 is 64 megabytes of cache on the chip. Now this picture here is actually a die photo of this chip. So all this stuff lives on a single chip. And this chip is about nearly 700 millimeters squared. So it's about kind of that big, like a very large postage stamp. They managed to cram, 4 billion transistors onto something that big, and 17 layers of metal. Pretty incredible. But here's the floor plan. So what you're seeing here, you're looking down on the surface of the chip, and it's only like half maybe a few hundred microns thick into the screen, but tens of millimeters across this way. And so you're seeing these are the cores. Where it says core 0, these are the microprocessors. These are the processors, core 0, 1, 2, 3, 4, 5, 6, 7. So inside each of these cores, they include these two levels of cache. So level 1, level 2, those are local to each core. And then level 3 is shared by all the cores. And you'll see the level 3 is actually in the middle of the chip, right? So it makes sense, just from, geography, if everybody needs to share something, the best place to put it is in the middle, right? So the L3 cache is in the middle of the chip because then that, on average, reduces the wiring delay from every CPU to get to that central cache structure, right? Now the next level out is the shared level 4 cache, and this is 480 megabytes of cache, and this lives on a single chip. And this is the plot of the chip here. And here you see the data part of the cache. And here what they call L4 dir, those are the directory bits, those are the tags. So dir is where the tags live. So notice the tags are in the middle, and all the data is spread out around the rest of the chip. Actually, you see here back on the CPU side, the level 3 tags are held here, and these are the data portions of the level 3 cache, right? Now, what you probably can't quite make out, but there's, on this edge are drivers, what they call the X bus, and that's how these chips connect to these chips. And so multiple chips connect to, you can have up to 3 of these guys connecting to one of these guys, and then those 3 chips are sharing that level 4 cache in the hierarchy. Yep, question? Right, so the question is, why isn't L4 in the middle of anything? Well, it kind of is at the next level up because this is a separate chip, so it's fabricated separately, and they put these together on a module, and on that module there'll be 3 of these CPU chips around that level 4 chip. So we're just showing one of the CPU chips here, and one of these chips, but there's actually another 2 of these will be arranged around this guy in the actual next level out of packaging, right? So there's an incredible amount of memory on here. One of the reasons they can have so much memory is that the small caches at the inside are built from what's called static RAM, and static RAM retains its value as long as you apply power, but it takes 6 transistors for every bit in that. To make 1 bit of SRAM needs 6 transistors. The rest of the memory is made from what they call embedded DRAM, EDRAM. This is like dynamic memory, so it actually needs to be refreshed. So each bit of that EDRAM is a 1 transistor and a capacitor holding charge. And it needs to be refreshed. So that's why it's called dynamic memory. If you don't refresh it, it forgets what bit it had. So you have to keep going through, reading and writing it again. But it makes it very dense, and that's how they can cram, half a gigabyte of cache on this 1 chip. Or how they can put 64 megabytes of L3 cache on just a piece of the processor chip. Okay, so this is a modern day example of 4 levels of cache in a commercial mainframe processor. Okay, now when you're talking about multi-level caches, it's important to understand the difference between what we call local miss rates and global miss rates. Okay, so a local miss rate is if I just take one cache's perspective on things. So locally, I look at what requests do I receive, and how many of those cause a miss in my level of the cache. Okay, just local to that one cache level. So for example, for an L2 cache, the local miss rate is the requests it receives are level 1 cache misses. So you access level 2 when you get a miss in level 1. So the accesses to level 2 are basically caused by level 1 misses. And so the level 2 local miss rate is how many of the level 1 cache misses miss in level 2. right? That's the local miss rate from the cache's perspective, right? So it's just locally observing how many requests are made to me, how many of those miss, all right? However, it's also important to understand the global miss rate, which is of all the requests made by the processor, how many of those ultimately end up missing in level 2, or whichever level you're talking about, right? So the level 2 global miss rate is the fraction of all references that miss in level 2. And the global miss rate is important because it usually tells you much more about the performance of the system, like how often does the processor miss in level 2 and have to go all the way to main memory. Usually sort of misses in level 1 that hit in level 2 are much faster and don't have as big an impact on performance. Okay. The other thing to realize is that the level 2 local miss rate is always going to be significantly bigger than the level 2 global miss rate, right? So remember that the level 2 global miss rate includes all the accesses that hit in L1. Those are considered hits too. So the misses are much lower if you look at the global miss rate. Whereas the local miss rate, everything that missed in L1, a lot of those will also miss in L2. So the local miss rate is always bigger than the global miss rate. So here's some actual data. I think this is from the textbook. So what this is showing you is this axis is different benchmark programs with different input data. And there are, I guess you can't see one of these curves. Well, it's not so bad up here. So there's these 3 curves representing level 1, level 2, level 3 miss rates. This is percentage miss rates on the y-axis. So first question, are these local or global miss rates? Global, local? Global, right? How do you know the global miss rates? How did you know these are global miss rates? Yep. Right. Level 3 is level than level 2, well, level 1, right? So every level is seeing fewer global miss rate. That's what you would expect in a memory hierarchy, right? Level 3 is less than level 2 is less than level 1. So you know these are global miss rates. Okay, so this is a system with 32K I-cache, 32K D-cache, 256K of level 2, and 4 meg of level 3. Another thing to note is how variable this is. Depending on which program you run, you're going to get very different behavior, right? So some programs do really poorly in the cache. Like this program is known for being very bad with caches. So it has over a 20% miss rate in level 1. Okay, that's huge. That's a huge miss rate. And even in level 3, it's still missing 5% of the time. That's a pretty high miss rate for a level 3 cache, right? Whereas some other programs, like this guy, Perl Bench, this is running a Perl program, has very low miss rate in all levels of the cache. So when you're analyzing a cache hierarchy, it's very important you have a good set of programs that represent your workload. Because if you look at any one program and try tuning for it, you're probably going to hit not such a great point if you look at all the other programs in the space. Another thing to look at is the difference between level 1 and level 2 misses varies a lot as well. Like, so some programs have almost the same level 1 and level 2 miss rates, right? This is GCC, the C compiler running, right? What that tells you is that whatever GCC's data structures it's using, they don't fit in level 1, they don't fit in level 2 either. And so it's only when you get to a big enough one in level 3 that the miss rate drops quite a bit. So level 3 manages to capture all the working set, right? Okay, some other ones that, level 1 is quite a high miss rate, but as you get to level 2, you actually capture quite a lot of the working set, and so the miss rate's pretty low, all right? So behavior varies depending on the program. So it's important to look at a range of programs with evaluating cache hierarchy. Okay, there's a lot of text on this slide, so let's just work through it. So the local miss rate is the fraction of references to one level of the cache. So for an L2, the local miss rate is level 1 misses, level 2 misses divided by the number of level 1 misses. So level 2 misses, the number of misses in the level 2 cache, divided by level 1 misses, because that's the number of accesses that are made to level 2, right? Now the global miss rate is the references that miss in all levels of a multi-level cache down to some level, right? And feeding that into the expression for average memory access time. So how do we calculate the average memory access time when you have say a two-level memory hierarchy? You still always initially, think about it here, time for a hit plus miss rate times miss penalty. So for level 1, you still have to always pay the time for level 1 hit. Then think about the level 1 miss rate and the level 1 miss penalty. Well, the level 1 miss rate is the local miss rate. The miss penalty, though, is now this expression, right? So the miss penalty for level 1 depends on level 2, and the average memory access time for level 2 will give you the miss penalty for level 1, right? So misses from level 1, looking level 2. So the average memory access time for level 2 is the miss penalty for level 1. So you just expand it out. So the miss penalty for level 1 is the time for an L2 hit plus the local miss rate in L2. How many of the accesses into the L2 cache cause a miss, times the penalty from L2 going out to the next level out, right? So just expand this thing out. So the miss penalty for level 1 is just the average memory access time for level 2, and so on. You can keep going to multiple layers. All right. I know you've been waiting for clicker time, so here's clicker time. So we showed this So we showed these curves earlier on, and we told you these were global miss rates. So you're now going to select what's the right answer for what are the level 2 and level 3 local miss rates. And to make it easy, I just asked the combinations really, is it less than or greater than or equal or roughly equal to 50%? And that's on average across all those curves, right? So from those global miss rates, you should be able to answer what are the local miss rates we're seeing in the level 2 or level 3 caches. And this is on average. So don't just look at one point, kind of scan across the curve to get your answer. All right, this will take you a few minutes. I just realized there's a bug on here. Thought I'd make it too easy. okay, just give you a few minutes to put the last few seconds to put the last few numbers in. Okay, so I'm going to flip projectors. Okay, so two favored options. I think I'll give you another couple minutes to talk about this one over your neighbors. Let's start this again. Okay, just a few seconds left. Get your votes in. Okay. Okay, so I don't want to change the projector over. So it was about 66% said D and about 30% said B. So first of all, how would you answer this? So remember that the local miss rate is the fraction of misses that the fraction of accuracies the cache sees that it misses. And for an L2, the accuracies it sees are misses from L1. So really what you need to look at is the ratio between, this ratio from here to here versus from here to here. So if we look at this point, this is roughly 15. You can just eyeball this. This is more than half of that. So the miss rate in L2 here is greater than half the miss rate of L1. And so that means that the local miss rate of L2 is over 50% for that one point. Right? But now if I trace this over, what I see is the L2 is actually, I would say, I didn't run the numbers, but usually it's more than half the miss rate of L1, right? Because that L2 line is usually more than halfway up the graph, right, compared to L1 miss rates. So, and if you look at L3 on the other hand, remember it's relative to L2. So L3's miss rate is usually, I would say, significantly less than half of the miss rate of L2. So the correct answer is D. So And you should be able to just do that by quickly eyeballing the ratios. Now, one thing to get in your head is, wait a minute, that L2 local miss rate is over 50%. So more than half of the axes in L2 are missing and going out to the next level. So what's the point of having an L2 that misses more than half the time? First thing to say is that's very common, right? Usually you'll find the local miss rates in the outer caches are very high, like over 50%, 50% or more, right? So why would you still have them? Say it was 50%. Why would you put in a cache with a 50% miss rate? Right, the answer is, so the answer is, you might have a 50% miss rate, but that means it's got a 50% hit rate. So half of those things didn't go out to memory, right? So the glass is half full in that case. All right. Okay, happy St. Patrick's Day. I'll let you look at